All right, good afternoon. Let's go ahead and get started. In Capstone, we want to have at least one scientific seminar, and usually we have multiple. This year we're kind of going to the edge of that in two ways. Because number one, this is our only one that's strictly a seminar. Everything else I'm going to make you do stuff. But today I want you to experience a long academic seminar and think about what it means. And I'm going to ask questions that's not totally disconnected from everything else, because number one, we'll be talking about combinations of fields, interdisciplinary type stuff, and we'll also be talking about things that might impinge on your personal statement. I mean, remember that the personal statement is not really to the NSF, it's really to me. And so I'm actually interested in more than the NSF is. And if you want to talk about topics like this, like Capstone is really about not just your major, but your entire general education, which means UCore, UFound, writing, all of that. And I had some of you in my writing class, so if you want to bring back something from that in the personal statement, feel free, because I'm looking at it from my viewpoint, and I'm very interested in that kind of thing. So what I'm going to do today is I'm going to give you, for most of the lecture, I am going to give you a talk. Do feel free to really stop me, and if you want to talk about different things, if you want to have questions, it's not like there's a set amount of stuff that I have to get through. It's not like biochem where we have a test at the end of it. This is more about how to integrate all the parts of your general education here, and I want you to keep that in mind as you are doing it. And one of the reason why I'm going to talk about this guy right here. When you say a theology book, you might not think of something with this title, or even this cover on it, or even this name. If you look at the guy's name, St. Maximus the Confessor, I mean, that's definitely on the end of the spectrum of interesting theological names. You know, he got his name. We went through a whole book with that. I went through this book, readings of it, with a whole bunch of other professors. It was led by Rick Steele. I'll tell you more about it in the talk itself. But I do, and I was pretty much blown away, because it looks like some kind of thing from the 60s or something like that, you know, cosmic. We don't even use that word anymore. I think they used to use that as that cool kind of thing. But it really does come from the Greek word cosmos, which is as big as it sounds. And so it's weird and big, and it's theology kind of unlike anything else I saw. So as I was going through this, I also got an invitation to go to Pittsburgh for the first time. And so Eric Long told me a good place to eat, and it was a good place to eat. I have to recommend it. If you're ever going to Pittsburgh, you want to talk to Eric Long. But I'm going to basically give you the talk. The conference is a weekend conference over President's Day weekend for a bunch of college students who are there for this campus ministry sort of thing. So there's a lot of college students that are thinking of going into ministry, but there's a lot of them that are thinking of being scientists. And they wanted me to come and give a workshop where I talked about what science was like for a Christian. And so I wanted to talk about St. Maximus. That's what came to mind when they asked. And so this is that talk that I'm going to do. I'm going to explain that because there's a few things, I referenced things in Pittsburgh. Has anybody been to Pittsburgh? Okay, so we got the old folks. Is anybody from Pittsburgh? Are you from Pittsburgh?
No, I went to, my college was like 45 minutes from there.
Okay, so you're native enough, like Eric Long, and Daniel Schofield as well. So anybody have family from Pittsburgh, knows anything about the area? I'm going to give you a little bit. If you know one thing about Pittsburgh, though, what is the major industry of Pittsburgh that went so far as to name their sports team after it? They got the Steelers, right? Because the steel industry was big in the Pittsburgh, and I went by it's like the first professional football games there. So there's a lot of, so I wanted to go into what that was, and I'm going to start there. So in your mind, you can imagine this is that setting, and I want to talk about that. So I would like to open us up with a prayer. May you be filled with the full knowledge of God's will, in all wisdom and spiritual understanding, to walk in a way worthy of the Lord, wholly pleasing, bearing fruit in every good work, and growing in the full knowledge of God. Amen. You might recognize that. It's Colossians 1, but it's David Bentley Hart's translation, who's also influenced a lot by Maximus the Confessor. Full circle. So, my first question is, you've come here to see a chemist speak. What is chemistry? Oh, and by the way, I should tell you your assignment at the end of this is going to be take notes as I talk about the things I talk and the order in which I talk about them and connections that you make. At the end of class, we'll have your assignment. It's going to be the typical thing where you take your notes and turn it into a 100-word thing. I'm going to give you a little bit more to chew on when we get to that point. But do take notes, okay? Because I want you to say, maybe you want to say, I started by asking what is chemistry. If I ask you what is chemistry, what image do you think should come to mind if I had to pick an image that represents chemistry? Let's go ahead and give me images. What comes to mind? The atom, okay. And what kind of picture of the atom do you have in your head? What does it look like?
Nucleus with a bunch of
Yeah.
powder on the outside.
And how are they moving? How are they depicted?
Fast.
Yeah. So, and that's actually really good. Our model even of the atom, if you say the atom, if you ask in ancient Greek, they would say a platonic solid in some cases, things like that. If you ask somebody before Rutherford, they would say plum pudding, and things like that. People have different metaphors for that. That's the great thing about chemistry. We use different metaphors to describe what the atom is. So even if you use language to describe the atom, just saying the atom is just the beginning. You have to say what the image means to you. Okay, so we've got the atom. Is there anything else that comes to mind when I say what is chemistry?
If I'm thinking of like early chemistry, we might have been looking at like people trying alchemy or trying mixtures and trying to figure out.
So what does that look like in your head? Describe the scene.
Reactions.
Okay.
And trying to make new things.
So little reactions, big reactions. What kind of reactions do you think of?
Explosive ones are great.
Everyone loves the explosions, right? You always have, and alchemists have always been known for their sooty, toxic, dirty environments that they work in. So chemists were always often put on the edge of the city because you like the fact that they promise you they can make gold for you. They don't deliver on that promise really, but they also can do other things for you. They can make paints and stuff like that. But they also explode sometimes, so you got to take care of that. Chemistry has an element of danger in it, right? Both good and bad. Any other images like characters, people who are chemists? I mentioned the Big Hero 6 chemist character the other day. Are there other characters who are chemists if you think of a chemist?
I'm going to think like a math scientist.
Yeah, so the math scientist. And what do you envision when you see a math scientist in your head?
Crazy hair, white lab coat.
Yeah. So always the white lab coat, which I never wear. Crazy hair, which sometimes I order on. So you have all the things, and no one scientist really. Einstein, when we showed Einstein, everyone loved the crazy hair picture of Einstein. But he didn't always have crazy hair. There was a time when he actually combed. So, yeah, so we have the mad scientist stereotype. Any more characters, specific or general, who you'd come up to if you think
Marie Curie.
What's that?
Marie Curie.
Okay, so yeah, you can have the historical character, and she's often brought up now because she's a great example of, she accomplished great things, and she was, despite discrimination and things like that, and that's a great story to look back on today. She also became very sick from her experiments, showing the toxicity of chemistry. Yeah, other characters who are chemists? Walter White and Jesse, right? Jesse is the grad student. Well, not really. He's not really a grad student. Yeah, Breaking Bad. And by the way, I've watched all of Breaking Bad, and I actually think Better Call Saul is better than Breaking Bad. But that's another story. We'll have to talk about that if you've seen them all, because spoilers. But yes, if you do a chemistry image search, you get the atom. You get this very bad model of the atom, which is now not believed anymore, but the planetary model. But hey, it's what we have in our head, and it explains what's going on. You have colored things, you have molecules, you have a chemist. I don't think that's Marie Curie, but it could be. And you have all these things. So when I was walking around Pittsburgh, And by the way, Pittsburgh has yellow bridges. It has a lot of them. I thought it had one. And then I go there and I find out it has like 4 or 5. So between 2 of the Pittsburgh's yellow bridges, you have this building. You zoom in, it's Alcoa. Anybody know what Alcoa makes? You can take the name apart and maybe get a hint. And it's a chemistry company. What product does Alcoa make?
Among other things, aluminum.
Yeah. So the aluminum is part of the Alcoa. I looked up what the name meant and I forgot now, but definitely it's aluminum is what they made. And so I was saying to the people in Pittsburgh that chemistry built this town a little bit. Here's Alcoa's processing plant for making aluminum. It's Pittsburgh-based, conducts operations in 10 countries now, and they take bauxite, which has aluminum in it, and they basically decompose it down to its components and get the aluminum out of it. They break all the bonds to everything else but aluminum, and they extract the aluminum. Now, there's very difficult to do this chemically speaking, strictly speaking. You do it electrochemically, because the electricity can help break the bonds of aluminum, the tight bonds of aluminum to everything else. And so it takes a lot of electricity, and that's what all this is right here. This is involved with the electrochemistry of breaking bonds. So if you think about the electrochemistry class, the electrochemistry part in your chemistry class is a small part of the class, but it's a big part of history, and it's part of the reason why Pittsburgh is Pittsburgh. So if we say, what is chemistry? I want to apply a more abstract definition of chemistry that can be more broadly applicable than some of these things. Less of a concrete image, but chemistry is about bringing 2 things together and making something new. It's about novelty of joining things together or of breaking them apart and analyzing what you have. So synthesis and analysis. If you think one of the first truly chemical reactions was that we made an element. They used to think water was an element, but you can break it down. And you can make water from hydrogen gas and oxygen gas, putting them together. You can take sodium metal and green chlorine gas and put them together and they make something very different and much less toxic and reactive. They make table salt. So sodium plus chloride makes table salt. That's definitely something new. Blue copper sulfate plus sodium carbonate, which is just washing soda, that makes green malachite, and this can happen naturally. So you can have caves with malachite stalactites in them. You can go through, and the carbonate runs through the water and things like that. That's all chemistry. I don't know if anybody has any malachite jewelry, but that's actually a copper carbonate. So then you have potassium chromate plus zinc sulfate in a basic environment will make yellow zinc chromate, which is not naturally made, because those reagents just don't come into contact in a large proportion to make the pure material. But we can do that in our labs. And if you have an antibody versus an antigen, that can make an immune reaction against a novel pathogen. That's what I do in my lab, and that's bringing 2 things together to make something new. So I like this understanding also because it's broad. It's broad enough to reach back in time to a 7th century theologian. And that's where Maximus says something that really reminded me of this definition of chemistry. To get to that, I want to talk about why I'm a chemist in the first place. Why does all this bringing things together and making something new, why does it really appeal to me? And where does my background come from? So this is a little bit of my own personal statement. And then I'll get to the point where I heard the 7th century metaphor that seemed to be very chemical in nature from Maximus. So I actually got started in science with the science fair. It is sort of stereotypical mad scientist kind of way of doing it, where you have a science fair and you find that you like doing that project, but I want you to have that same kind of attitude with your grant proposals, because those are basically like a science fair project. It's just for grad students that last 5 years. So you want to be thinking about that. And eventually I was a grad student, and long story short, I ended up at the University of Washington. And Mr. Regan, by the way, was my mentor who set up he had his whole classroom to help students do science projects. He had a whole room for it, and he basically had a dedicated lab. And that allowed me to do that. I would not have had the impulse to do it on my own. And so I ended up going to grad school and publishing that dissertation right there, which is how two things come together. This just happens to be an immunological protein and a peptide that binds to it. But from 7th to 12th grades, each year for 6 years, I took the course called Science Research, and that made the space that allowed me to ask the questions. Now, it always stressed me out coming up with the topic. And so you might be feeling a little stressed out coming up with the topic for your own thing, but all I've got to say is it is part of the deal, and what you have, you can make pretty much anything work if you just apply your scientific knowledge to it. And we'll talk about that. We'll go through the process. So I just remember my own stress when I was in your shoes for science fair projects, but I want to say that's part of the process that we want you to go through. We don't want you to be stressed. We want you to get through it. It's that kind of thing. And it ended up being, so that was research done in a teaching thing. It was research and teaching brought together. The science fair project was a little mini research project, right? But it was in a class. Then I went to University of Florida as an undergrad. I had a dual BS, so I brought together two things to bring, I got 2 degrees that I brought together. One was in the College of Liberal Arts and Sciences in chemistry, as you probably could guess. The other one was in public relations, which had a subset called technical communications. And so I got a journalism degree. That was in the School of Journalism. I got my worst grades. I got better grades in chemistry than I did in journalism, but it's not about the grades, right? It's about the experience. So then I started graduate school at the University of Washington in '96. I started attending Bethany Community Church. And by the way, Bethany Community Church, you might drive by it when you're at the northwest end of Green Lake. You might see this chapel there. And one fun fact about how we got into the news nationally once was our church was actually struck by lightning once. They were actually having a worship band practice inside there, and they were apparently playing the song, "God, Let Your Fire Fall Down." So you might want to, I don't want to scientifically put all that together, but I think God does have a sense of humor. No one was hurt, by the way. You can still see the little painted over patch, by the way. I show everyone when they come to that building. But I chose a church, and I also chose a PhD advisor. And I chose one who was very good at both research and teaching. I talked about him a little bit the other day. He was a structural immunologist, and he dealt with the kinetics of these things. And so I found out that this worked for me. And this is a figure from my dissertation. It's also published in one of my papers. That's the way that usually it works. You publish both ways. And computer graphics have improved a bit since then, but this shows that I was interested in see those dotted lines? Those hydrogen bonds. I was asking, how do they work? I take them apart, and I see how the molecule comes together, how an immune response is started. So again, it's bringing two things together and making something new. So then in 2003, I started teaching and researching chemistry. This is my favorite picture of it. The logo changed since I've been here, but it's the same place and location, and I've had my own lab right there at the foot of the hill. And in the lab, I do research and I do teaching as well. I mean, many of you have taken a class with me, and you've technically been part of my research group in a small way when you do that. Because it's what I like to do when I teach the research. Now, the problem with doing research in the classroom is it actually scares a lot of the teachers who want to do it. And it is a scary thing, because it might not work. That's the whole thing about research. It might not work. And it didn't work. There were ways to know I was wrong as I was going along. But I kept trying to figure out, well, if you're wrong, what does this tell you about what's actually true? And then it turns out that wrong can be an open door to the truth in some ways. My first hypothesis was completely wrong. And then we found out that if we did the opposite, we actually made it work better. We thought we should stabilize. It turns out we should have destabilized. So we destabilized, and we published that paper. These atoms are super special. If we change them, the whole thing will fall apart. But there was one case when we changed the atoms, and it actually worked better. So we thought it was optimized, but it was not. And then we should follow, I was making new proteins. We should follow this protocol from the people I don't know. And it didn't really work that well. And then I ended up finding out that I had a protocol for people I do know and trust. And they gave me the protocol and advised me on it. So you should go with that. That's sort of a life lesson. And then there's some ways in which you can be wrong in a good way. Like I was making proteins that I was hoping in some cases would be a faint orange color. Maybe a few of them would be faint orange. And then when we purified them, we found a faint orange protein, but also a bright blue, a bright pink, and a bright yellow protein. I still don't know exactly what's going on because I've had to move on to another project, but that's the kind of thing where being wrong can actually be good. So don't be afraid of being wrong all the time. You want to be as right as you can or see it as a door to another direction. So basically we were all tested, and I wanted to refer to this because I actually had spoken at that conference before in 2021, but they were all remote, and I was speaking to Zoom. I didn't even know. They told me there were 80 people in the room, but I didn't see a single one of them. I think I got a few questions at the end, so that proved that there were 2 people there. But I had done the Jubilee conference before during COVID, and I wanted to go back to when I was doing that because this was their first one to be back together in Pittsburgh in the same place. And so I wanted to tell them the story that I told then was how I integrated research and teaching when COVID hit. Number 1, we had to be online. Number 2, I wanted to teach with research, so I came up with a computational research project where we looked at the cross-reactivity of the common cold with SARS-CoV-2. And it turns out there's moderate cross-reactivity, and it turns out there is some moderate long-term protection, not at the antibody level, but at T-cell level. So this probably mitigated some of the worst effects, but you couldn't stop the pandemic, obviously. It did give a little bit of hope that at least this wouldn't be like The Walking Dead, okay? And as much as it was, people needed hope at that time. And so this gave us a little bit of hope, but you also want to be clear, it's 1/3 similar that you can get some cross-reactive immunity from, which is not even half, but it's something. And so science communication of all that. But that's how we combine science and research when we couldn't actually even get in the lab, because you can do this computationally. This is about how the sequences are similar. And actually I had to decide, because I was doing it on a computer, I had to decide what level of similarity is enough to say, yes, this is similar, versus no, this is not similar. And at the end of the day, I had to look at the papers and guess. Now I had a bunch of papers that showed, and if you look up and down these, in general you see that you have some cross-reactivity between SARS-CoV-2 and common cold coronaviruses at about the 1/3 level. But of course the numbers are all over the place. These are different studies with different powers and things like that. But this is the same kind of thing when you're looking at the literature and coming up with your own project. One of your projects could be looking at literature like this and saying, we think there's some cross-reactivity, but not a huge amount, not a majority cross-reactivity, but maybe some, like 30%. And so that was based on these. These all came out earlier, and basically I had to decide what the threshold would be. And I decided on a certain threshold. I think it was 50% for this particular threshold. This is not the same exact thing of the 30% I was saying. But all that is to say, I had to take a guess. And what I found out later is that the guess was basically right. It was from one of these same groups published an actual data where they tested what the threshold was. And the threshold ends up being exactly what they had projected it would be. And I trusted them, so I took their threshold and it was proved right. It's kind of cool in science where you can make a prediction because you can be wrong and that can worry you. But then sometimes you find out that your prediction trusted the right people and trusted the right data, and it ends up being right. So the other thing is, outside the lab, I actually had an interest in chemistry and evolution, and I wanted to explain how I thought chemistry and evolution work together. Again, two things that you might think are different coming together to make something new. And that is all, as a believer, I believe that's all under the providence of the Creator God, who is transcendent and above all and made all things. What does that mean exactly? Well, I wrote a book to try to think about that. And even writing a book is an act of faith, but I kept worrying about what if new findings found out that would prove me wrong. And by the way, I had to write a grant for this. You have to write a grant for everything. So what you're practicing in grant writing is actually a very useful skill. The book eventually got translated into 3 languages. 2 languages. One of them never came out. The Russians never actually, they paid me for the translation, but they never actually came out with it, as far as I know. So Chinese and Japanese, if you want it in your native language, you're in luck. And we also translated the Japanese version. Here's the Japanese periodic table. Of course, we kept the Western letters for all the below things, but everything else got translated. And I actually worked with a translator for Japan. China, they just gave me someone, and then they sent me the book one day and said, hey, here's your book, here's some money. Thanks, not much money, but you don't care. It's translated into Chinese. So the story about this is that is how chemistry and evolution went together by the chemistry of the different elements giving them an evolutionary role, a biochemical role. And the thing is that they were divided up into 3 different roles: balance, building, and catalysis. And by the way, there are some things you see like here you can have half and half. You can have one element filling more than one role. But the interesting thing about this is if you look at here, in general, you have 1 or 2 elements in each of the columns of the periodic table. Almost like if you have one here, you don't need another one. You also have stuff near the top of the periodic table. All of this has a reason for, chemically speaking, why it should be this way, why life selected these elements and then didn't select, holmium or whatever that says, lanthanides and things like that. So you have a limited set, and these are all the elements there are. So the idea is that you had a restricted set of possibilities, and that means that evolution was not just anything could happen. At some levels, anything can happen. You have random mutation, and that can be very, very important. But at the chemical level, you can't use boron for life. That's part of my proposal. You need to use carbon. And so these elements were selected from the 90 natural elements, and they were selected for their particular jobs. You're kind of looking at the same thing. Here it is colored with red, green, and blue. And these jobs are taken by the different areas of the periodic table even. You use the middle of the table for catalysis. You use the top of the table for building. And there's reasons for all of that. You need a lot of the stuff that's built, and the periodic table is abundant from the top down. Therefore, you have to use stuff on the top to build your organisms. It's that kind of reasoning. So, and even the periodic table came out of physics, so I do have to say that underneath it all, before there was chemistry, there was physics, because you can't really say there was chemistry before there were, free electrons and different elements in the periodic table itself. Big Bang gave us a lot of hydrogen, a little bit of helium, a tiny bit of other things. And then from that, those recombine to become everything else that we see around us. We know the processes of these. The stars made different elements, and the heavier, the better. The stars like to make iron. Iron is the most stable nucleus. And so we end up, if we come to equilibrium, we're able to get to that, we're able to make a lot of iron, and it sticks around. But there's a lot of time that it takes to go through this process. And the thing about this is the stars are bringing things together and making something new. The stars are sort of the factories for the new elements. And you can talk about all the cool nuclear chemistry. I think that we can argue about whether this is physics or chemistry. I think we're getting into nuclear chemistry at some point when we're talking about building up the elements in the heart of the stars. But all the borderlines are blurry anyways. Okay. So you have the truly new elements being made all the way up to gold, which is made in supernovas. True story. And basically, you realize that you can say you've probably heard the "You Are Stardust" type thing. You've probably seen Rogue One and things like that. But the whole thing is that I want you to realize just how weird this would seem to an ancient person who is sitting there looking at the stars, and they seem so different. It seems like there's and there is a difference, right? There's a huge distance between us. But in terms of atoms and material, we actually share a material origin with them. And that is meaningful. So heaven and earth are brought together. So I already talked about this, but basically the certain abundances lead to certain uses. And you can see that all of the building things are abundant, all the catalytic elements are less abundant. And then because you're building everything up from hydrogen and helium, you have a lot of the smaller things, but the bigger you get, this is abundance of the total atoms in the universe, probably has some error in it. But if you look all the way out here, you can see once you get past copper, you really don't have as much of everything. I honestly should pull out molybdenum because it's actually used for catalysis. That should be colored blue in your head. There are minor exceptions. But in general, the more stuff you have enough for life to use it, and life doesn't use the rest because it's not available. If it's not there, you can't use it. And there's chemical reasons for this. So the green elements, carbon, hydrogen, oxygen, and nitrogen, basically they're what you are familiar with from biochemistry. It's what we build our bodies with. And those are brought together to make new shapes, to make all the abundance of carbon-based organic shapes. And you all know organic chemistry. You've been through the complexity of carbon. I don't have to tell you more about that. But the thing is, that's bringing together carbons to make a new shape, make a new organism. And so the thing is, and again, many of you have taken these classes. In the classes, we bring together research and teaching, and we bring together different chemicals to make new proteins. And in fact, if you are curious about that and you weren't in my class, we have some people who are going to be presenting that at the Erickson. So I encourage you to look at that. But basically, fall, winter, spring, there's a sequence of classes where we design proteins, make proteins, and test proteins. We're in the middle of this right now. There's another way in which I do it. That's the way that I bring together research and teaching at the upper division level. At the lower division level, we bring together research and teaching by making pigments. There's another thing that alchemists do, right? And so here's one of the things that we do. We take zinc sulfate and potassium chromate and mix them together. I believe this is very soluble. But when you mix these together, it makes an insoluble bright yellow precipitate that sticks, you can see it in that tube. What you're doing is you're bringing the zinc and the chromium together, and you're making a new insoluble yellow pigment. Now, if I had to ask you, people have been in my class, no fair cheating. I want to ask somebody who hasn't been in my class, if you see this color, is there a particular artist or even artwork that color reminds you of, who loved this color and used it all over the time? Very famous artists, famous paintings. You guys want to guess? That's it. This was invented in the lab. He used it. It was made cheap enough that even a starving artist could do it. And Spencer Van Gogh's sunflowers are made of chrome yellow. Technically, his used lead as a counter-ion, but we make this safer by including zinc, which has the same properties, a lot less toxicity. So we try to watch out for you guys. And this is what it looks like. This is the lead chromate being made. We use mortars and pestles, and you can tell we have dedicated mortars and pestles because we make them all colorful, and we can't get the color completely out. But then we have a little vial of the pigment. Right here, this is red madder, which is actually a medieval recipe. It's even ancient Roman in some ways. But it's a way of making a pigment out of a dye. And so we do that as well. And this year, by the way, each year I learn a little more about doing it because honestly, when I started, I didn't know anything extra about this, and I was worried that it wouldn't work, and then it did work. And we figured out, Sue Martin helps figure out each year how to make the red a little brighter. And this year we got really bright red matter. So you can see our learning throughout the years. And that's research and teaching. I do want to say, I talked to some people about doing a teaching project for your fellowship. That's a really good idea. And you can do something like this if you can measure how the students learn. You want to have a new idea that you bring to the students, a new way to do the class, and then you do this. So I just want to say that, yeah, you're welcome to do that as well. There's so much color left over. Your waste beakers are very colored, and you can see the different waste from the different parts that you get. That's how much color you make. Color is something that chemists can make. Now, when I said that this doesn't occur in nature, it's sort of true. You actually do find some lead chromate in nature, but it's not yellow. It's not chrome yellow. It's this. For some reason it's a red saffron color. I'm actually not sure why, because I can't find a reason why it's red rather than yellow. The natural red chromate is this color, and it was found in 1797 by a chemist who analyzed and found that it was a new element, chromium, in there. So this is great, but this is rare. We can make buckets of it in the lab now, and because we could make so much, it was cheap enough for Vincent van Gogh to use. And so I like to think of chemistry as facilitating Van Gogh's creativity in some way, although definitely Van Gogh gets most of the credit there. So this is where the chromate is, and this is what I already mentioned, that we used because they used to use lead, but now we use zinc. Oh, and by the way, Vincent van Gogh chewed on his paintbrushes. He used lead chromate, he chewed on his paintbrushes, he cut off his ear for mysterious reasons. He had challenges to go through in life, right? He always fought with his roommates, I mean, who doesn't? But he wasn't the easiest guy to get along with. Some people wonder if the paints affected his health, not just physically, but also mentally, because lead does affect your brain. And so, at the same time that chrome yellow unlocked his creativity, the toxicity of it also was a danger, sort of a double-edged sword. But because of his creativity, he made paintings that are still worldwide recognizable. By the way, if you are a fan of Vincent van Gogh and Doctor Who, you probably are familiar with the Doctor Who Vincent episode. If you're not, it was one of the first ones that I watched, and it's a great thing about Vincent as a person. But you can look at this, and you can see the sunflowers are what everyone knows, and people even mimic it. We probably have AI replicating this right now. But it's still the spark of the creativity, the novelty came from Vincent. So how do we understand this? There was a gift given to Vincent. He gave the gift back to us in the form of the sunflowers. Here's a zoomed-in look at it, and you can see there's a chemical behind it, but then there's an artist that made something genuinely new. His thing was bringing together images and making a new image from that. And I would also argue it's an open question, can computers even do this? But computers can do something, they can do a lot. But what's the nature of the creativity? Now, the other thing that happens is now some of the colors are browning. Chromium yellow will actually turn brown under certain conditions. Well, as chemists, we can figure out why it's turning brown and stop it so that we can preserve the beauty that Vincent painted for future generations. And that's a calling. By the way, if you have a calling, if you have an idea, you have a purpose, you have a proposal. And so all of these, everything that you look at, you can turn into a proposal. So that's a long way around to talk about how we talk about bringing things together. But the reason why I did this is the metaphor of bringing things together to make something new is exactly what Maximus the Confessor produced. Now, this is the class and reading group I took with Rick Steele. Hopefully, you've had a chance to take a class with him because he is retiring at the end of this year, which is sad, but I hope to do things like reading groups to get him to come back once in a while. And so this is what Maximus wrote. He said, "Humans are above all like a most capacious workshop containing all things." And if you look at that has ergosthene, I believe it is, ergostheon or something like that. But the important thing is ergo. If you hear ergo, you think like ergodynamic, you think like working. You might think of the the unit of work. And that's where this work contains a place for working, which is a workshop, or in Latin, a place for laboring, a laboratory. And I'd completely lost the fact that this is what, when I say my lab, I forgot that labor is part of lab, but it really is what it is. And an artist has a workshop as well as a scientist. And in the workshop that he's thinking of a workshop where an artist brings things together and makes something new. But I think it applies just as well to a chemistry lab because it's even the same word. And we're bringing together things to make something new. And it's a lot of work. And he says that every person, if they have an official lab or not, in your mind and in your spirit, you are kind of a workshop or laboratory. You're bringing two things together and you're making something new as you live life and you discover things, good and bad, and you bring that together into your experience of what is going on. And that is one of the purposes that God made you to fill. So bringing together, and he talks about nature is divided into heaven and earth. The workshop, the human in the workshop, brings together heaven and earth by understanding heaven down here on earth. So we talk about that with chemistry and stellar nucleogenesis, or when Dr. Lindbergh talks about relativity, we're understanding how the heavens go, as Galileo said, right? And that's bringing together heaven and earth. That in itself is a good thing. It reunites what once was broken. It overcomes ignorance. And so your soul and your learning and your job as a student earning a degree is actually part of what St. Maximus would say is a good vocation to bring together things that were broken apart. And if it seems like work, that's because it is. But that's what the work of a scientist and the work of a student in science is going to be. So how does the biochemist know about Maximus the Confessor? I told you about Rick Steele, and in the reading group at the same time, because it was a Greek Orthodox writer, we had a systematis focus come, Dr. Lindbergh's old colleague, who is now in California, but he was able to zoom in. We had Katie Kresser. I don't know if any of you have had her. She's a wonderful writer. And of course, everybody knows Eric Long in this room, I'm sure. We had all these people coming together in one room, and to me, this is also bringing things together, bringing together the biologist and the chemist and the physicist and the theologian and the art historian, and making something new in our own discussion. So this also applies. So Maximus the Confessor lived a long time ago. You know, you can see he lived in the 680s. And he's the confessor because he was almost martyred for his faith. He basically had his tongue cut out and his right hand cut off because he did not bow to what the emperor said was true theologically. He went from his own reasons and convictions. The emperor didn't like that, so the emperor punished him. And he did not die right away, so apparently you have to die right away to be a martyr. He died like a couple months later. So that means he is a confessor, not technically a martyr, but we all know why he died. After he died, pretty quickly, his teaching was approved. The emperor's way of thinking went by the way, and his thinking is now orthodoxy. So he has a really interesting, and this is he wrote these passages. These are letters that he had. And he has an idea, his whole idea is about the universe in a space of becoming. So I want you to see this quote. The created nature received its being through a process of becoming. Basically, it's not just like poof, everything's here. He says it's important that things take time to grow and develop. That the Word of God started with Adam and then went through Jesus and then came to us. And that took thousands of years. I don't think he would have a problem with the idea that life started 4 billion years ago and then took 4 billion years to get to us, because honestly, who's counting at that point? You know, who's around to be bored? So I see in him, I see a theology that can really fit together well with the idea of an evolving nature. Maybe I'm wrong, but I think I have support from him against other people who would argue with it. And so let's have the argument. You know, that's my attitude. This thing about process of becoming comes from a quote from Gregory of Nyssa. The natures are innovated and God becomes man. He's talking about Christmas. He's talking about innovation. Natures are instituted afresh, but I love the word innovated, because when I say innovation, you think like Apple, IBM, or IBM's not really doing stuff anymore. But you think, if you gave me names, you would think of like all the companies want to innovate, right? Gregory is saying the original innovation was the incarnation. And Maximus expanded on that with this idea of an evolving nature where to move and to become is to be. So this innovantur naturae, natures are made new. This is a very famous, I think I have it circled here. Yeah, you can see it in the Latin. If you know Latin, sometimes you can get back to the original and you can see a shade of meaning that might be obscured in English translation. Right here, if you sing this hymn, you would see that innovator is in it. And you would see that Christmas was the original innovation. And so Gregory and Maximus were both like, what was going on here was a joining of divine and human, because Jesus was fully God and fully human. This is one of the things that Maximus died for this sort of orthodox theology. So what does it mean to me as a scientist in the 21st century? Well, I believe that we learn by participating fully in the world, just as God participated fully in the world in Christ. That means that we get our hands dirty. That means that we work and that we do things that are risky, that don't always work. The labs don't always work. I'm sorry, but that's my calling. You know, it's that kind of thing. And I've got to remind myself when the lab doesn't work, okay, well, I'm still finding out something new. We're participating fully in the world, even though what I wanted to happen didn't happen this time. So I want to return to a David Bentley Hart translation. Remember this, Colossians was what I opened with. I did that for a reason, because Paul writes about the innovation of Christ. In Christ, all things hold together. So the universe was made, including the science of how things hold together, which is chemistry. So I want to say that this is a chemical understanding of this verse, because in him were created all things in the heavens or on earth, the visible as well as the invisible. And right here, at the end of the poem that Paul writes, whether the things on earth or the things in the heaven, he's putting this idea of joining heaven and earth at either end of his poem. And so this idea of reconciliation, I'd even extend this. Part of the idea is the idea of restoration. And I think even art restoration, the idea of restoring a browned Van Gogh painting, is an act of reconciliation in some weird level, you know? Not completely, but nothing we do is complete. So, yeah, I go through a little bit about what Paul's pulling from. He's pulling from the Hebrew Scriptures. He's pulling from Genesis 1:2. He's pulling from Proverbs 8, and he mashes them all together in that poem, Colossians 1 poem. So he himself is bringing things together, and that's what poetry does. So if you've had a class in poetry, you've actually had a class in bringing two things together and making something new. Two words together. So this is a little bit more about that, but I don't really have that much about it, except to say the firstborn of creation. There's actually a Japanese word for firstborn. It is Ichiro. So if you all know Ichiro Suzuki, he was a leadoff hitter for the Mariners. He was the firstborn in his family, and they all called him Ichiro number 1, Ichiro Ichiban. But that is the idea of being first, and then that goes with the idea of human and divine being brought together in Christ uniquely. Okay, so there's lots of beginnings in there. Unfortunately, I just want to circle them. These words are all very much more similar in the Greek than they are. The red words are similar in the Greek, and the green words are similar in the Greek. And they look like a lot of different words. But when you see into the Greek, you can actually see some things that Paul was doing, because he was writing in Greek, and he meant to do that. So we just want to say, and Paul puts at the center of it the origin, firstborn of the dead. And so you have the Easter Day resurrection of Christ as being a huge part of this whole thing. So we talked about Christmas, we talked about Easter, we're talking about all these things sort of happening at once, and that is the way that Maximus looked at it. So, the whole thing is that this is a case of irreducible novelty. And that's why I want to say, you might have heard of some people arguing against evolution by saying, what we have in life is we have irreducible complexity. And I actually have a piece that I've written where I argue against that. And I say, what matters is not irreducible complexity. And our faith does not require us to look for irreducible complexity. It requires us to look for irreducible novelty. And so we'll see if it flies past the reviewers. But the idea is that creation, irreducible novelty, the power of making new. God is the origin of all this. We are able to make new things as sort of like children playing with toys that are imitating their father. And that's the idea of what's going on with these quotes. So I just want to end with this idea of chemistry bringing things together and Jesus being the exemplar of what brought things back together, and he himself was brought back together physically. And now his life is at large in the world. So in response, that's why I want to say participate. Think about what problems you are called to solve. And think about the way you can apply science to systematically address those problems. And it won't get you all the way there. But that's the whole point. It should fill up a 2-page scientific proposal is what I want to see from you. Okay. So that's your assignment. Write a 100-word reaction to this talk. If you have like a question that you were going to ask, but we ran out of time, as always happens, feel free to write that question. This is also on Canvas, by the way. But so don't forget to connect it to your You Found You course if you can. I tried to do some of those connections. And my question for you, what does irreducible novelty mean to you? Consider your own history and how this applies to your personal statement. And thank you for your time. And next week, oh, by the way, next week there is an assignment, like a reading. I want you to have an outline of your irreducibly novel idea. It only has to be an outline. We will share that idea. Look for more details online. It's all on Canvas right now. Okay? So I'll see you next week with your ideas. Yeah.
Are you going to push this out?
If you want, I can put it. If I forget, remind me.